kids, I'm Professor Sponge. Today on Absorbent Learning, we are going to be talking about one of my favorite sea creatures, the octopus. We have with us today a fine guest, a nice octopus specimen. You will notice his defining characteristics: 2 well-developed eyes, a large head, 8 tentacles, and bilateral symmetry, which means that you could split him down the middle and he would be equal on both sides. Now you may ask, what exactly makes up an octopus? Well, every life form on Earth, you and me and everyone else, is made up of schnapps. That means carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We're talking about octopi today, not just because they look so weird, but because they act so weird too. Octopi are commonly referred to as the chameleons of the sea. They can change color incredibly fast, and it's not just like the red flushed cheeks you get when you're embarrassed. They can make any kind of background color that they choose, for protection, for hunting techniques, and possibly even for octopi communication. Here we're going to look at some fine examples of octopi camouflage. Oh, look at here, a nice horse race. That's usually not where octopi hang out, but oh, what's this? Look, an octopi is swimming by. Now we're at a Venetian palace. I don't think octopi belong there, but oh, what's this? Oh, look! Another one! What a weird place for an octopi to hang out. You think you're sitting down to a nice hot dog meal, when suddenly... an octopi! It was really an octopi! What amazing camouflage you have! You may think this is a crowd of happy Obama supporters, but really... oh! It's an octopi's home! Last but certainly not least, we're at a Rolling Stones concert. It appears, but what's this? Mick Jagger's face is moving and oh, suddenly it swims away. It was an octopus too. What amazing camouflage. As you just observed, octopi can undergo some amazing feats of camouflage. You may be like me and ask yourself, hey, why can octopi change colors, but I can't? I mean, I'm a sponge. I'm pretty cool. But I'm not equipped with chromatophores. They are pigmentary cells in the epidermis. They differ from a lot of other pigmentary cells because they are neurally controlled. This means that your brain sees a color, it tells you, hey, I want to be that color, and the cells turn that color. How exactly do chromatophores work, you may ask? Well, let's use this creepy fish's mouth as an example. Say my hand is a chromatophore. Inside, you have the pigment with an elastic sac around it. When this contracts, you see less of the color. As it expands, you see more and more. Here we have the basics of how these colors change so rapidly. Chromatophores are responsible for the reds, yellows, and browns in an octopus's color scheme. Other pigmentary cells, located beneath the chromatophores in the skin, are responsible for the crazier color schemes. These include iridophores, which create the metallic pinks, yellows, greens, blues, and even silvers. Then even beneath that, there's lucifores, which reflect light. Right now we're going to go into a little section I like to call the physics of colors. Now this gets pretty deep and pretty crazy and questions everything that you know. So if that sounds like too much, you might want to take a break. Alright, so we're going to start with a description of my favorite color, green. Here we have green paint. Yes, well, you may think it's green, but really, the pigments are absorbing every color but green. So you see this green. It is not green. It is purple. It is red. It is blue. It is orange. It is everything but green. But green is what we see it as. The same is said for red. Yes, it looks red, but that's not what its particles would tell you. All of the pretty colors are part of the electromagnetic spectrum. They're in the category of visible light, which ranges from 400 to 700 nanometers in wavelength. Now our eyes have 3 cones in them: green, red, and blue. They see these wavelengths and tell the brain to interpret them as certain colors. That, my friends, is why you see colors. Cephalopod ink can be used to scare away predators, or just when the cephalopod, here octopus, feels threatened. They can either be ejected in clouds or pseudomorphs, which are a more solid form of ink. Ink is typically composed of amino acids, melanin, and products of tyrosinase's enzymatic metabolizing. This creates the rather toxic stuff in the ink. The amino acids I talked about before include taurine, aspartic acid, glutamic acid, alanine, and lysine. Wow, that sounds like a lot of crazy stuff. I'm kind of glad I'm such a simple little sponge. I don't have to deal with all those different things. Now we're all in for a treat today, because with us here is the Picasso of the octopus world. He paints with his ink, and today he's going to give a once-in-a-lifetime close-up look to creating his splendid artwork.